Imagine you are a teacher and you need to line up your students by height. Shortest on the left, tallest on the right. How do you do it? One simple approach: walk down the line, and whenever two students next to each other are in the wrong order, sweep them. Walk all the way to the end, then go back to the start and do it again and again until nobody needs to move. That's exactly what bubble sort does, and today we're going to understand exactly how it works in pseudocode and in C++. Bubble sort is one of the simplest sorting algorithms. The idea is this: we look at pairs of adjacent elements, meaning elements right next to each other, and if they are in the wrong order, we swap them. For example, imagine we have this array 5, 3, 8, 1, and 4. We start at the beginning, compare 5 and 3. Is 5 greater than 3? Yes. So we swap them. Now we have 3, 5, 8, 1, and 4. Next, compare 5 and 8. Is 5 greater than 8? No. Leave them alone. Compare 8 and 1. Is 8 greater than 1? Yes. Swap. Compare 8 and 4. Swap. Notice something. After just one 4 pass through the array, the largest element, 8, has moved all the way to the end. It bubbled up to its correct position. That's where the names come from. We repeat this process, pass after pass, until the whole array is sorted. Let me show you the pseudocode first, before we write any C++ code. We have two loops. The outer loop controls how many passes we do. We need at most n-1 passes, because after each pass, at least one more element is in its final position. The inner loop does the actual comparisons. Notice it goes up to n-2 minus I, not all the way to the end. Why? Because after pass number I, the last I elements are already sorted. We don't need to check them again. Now, there's a smarter version. What if the array is already sorted? With this basic version, we'd still do all n passes even when there's nothing to swap. Wasted work. The fix is to use a flag. I'll call it swapped. Think of swapped like a signal light. At the start of each pass is red, meaning nothing happened yet. The moment we do a swap, it flips to green. Yes, something moved. At the end of each pass, we check the light. If it's still red, nobody moved. The array must already be sorted. We stop immediately. Let me show you the difference with two examples side by side. On the left, we start the first pass. We compare 5 and 3. Swap. The flag turns green. We continue the pass. More comparisons happen. The pass finishes. Flag is green. So we go to the next pass. On the right, a red is already sorted. We start the pass. Compare 1 and 3. No swap. Compare 3 and 4. No swap. All the way to the end. No swap. The flag is still red. We hit the brake. Done. Just one pass. That's big O N. This is the power of a one-line optimization. The swap flag turns a worst-case algorithm into something that handles sorted imperfectly. Now, let's write this in C++. I'll build it up piece by piece, not all at once. We start with the function signature. Bubble sort take two things: the array and its size. It returns nothing. It's stored in place, modifying the original array directly. The outer loop, each time this runs, we do one full pass through the array. we only need n-1 passes at most, because after each pass, the largest unsorted element is already in place. Here's our flag, just like in the pseudocode, reset to false at the start of every pass. In a loop, it goes up to n-1 minus I, shrinking each pass, because the last I elements are already sorted. Compare the current element with its neighbor. If they are out of order, we swap. Now, how does the swap actually work in code? Let's use an analogy. Imagine two people. A is holding orange juice, B is holding water. They want to swap strings without missing a single drop. They can't pour directly into each other's cup. That will destroy the first value the moment you override it. So, step 1. A pours the orange juice into a spare, empty temp cup. In code, let int temp equals array j. We save the value before we touch anything. Step 2. B pours the water into its now empty cup. In code, array j equals to array just plus 1. Array j now holds what array just plus 1 had. B's cup is empty. Step 3. The temp cup pours the orange juice into B's empty cup. In code, array just plus 1 equals to 10. The original value of array j lands in array just plus 1. The web complete. Nobody loses a job. That's exactly what temp does. It's the extra cup that makes the whole exchange possible. That's exactly what these 3 lines do. Temp is the extra cup. Without it, we'd lose a value the moment we overwrite. Flag turns green. Something moved this pass. After the inner loop, if the flag is still false, nothing moved, already sorted, we stop. Now, let's look at how we actually use this function. We create our test array and store its size in n. One line, that's all it takes to sort the array. And we print every element, the output, sorted 1, 3, 4, 5, and 8. Now, let's talk about time complexity, how the running time grows as our input size grows. Best case, big O n, with the swap flag. If the array is already sorted, we only need one pass to confirm nothing moved, and we stop. So, best case is just big O n, linear time. For a random input, we still expect about n squared divided by 4 computations, still quadratic. Imagine the array is in reverse order, the absolute worst case for bubble sort. We need to do almost every possible swap. The outer loop runs n-1 times. The inner loop runs roughly n divided by 2 times on average. Multiply them together and we get BO n squared. That's slow for large inputs. The space complexity is big O1. Bubble sort sorts in place. It doesn't create a copy of the array or use extra memory proportional to the input. Just a few variables like I, j, and temp and swapped. So, space complexity is big O1, constant. One more thing, bubble sort is a stable sort. What does stable means? If 2 elements have equal values, a stable sort keeps them in their original relative order. Bubble sort is stable because we only swap when array j is strictly greater than array j plus 1. We never swap equal elements, so the original order is preserved. So, Should you ever use bubble sort in a real project? Honestly, almost never. For large data sets, big O n squared is too slow. Most languages has built-in sorting functions, like stdsort in C++, that use faster algorithms like intersort or timesort, which run in big O n log n. But bubble sort is still worth knowing for two reasons. First, it's the easiest sorting algorithm to understand and trace by hand. When you are learning how sorting works, bubble sort is a perfect place to start. Second, it introduces a key idea in algorithm design, that a small optimization, like swap flag, can dramatically change the best case performance. Understanding bubble sort teaches you how to think about algorithm, and that skill transfers to everything else in computer science. Alright, that is bubble sort. We covered what it does, the pseudocode, the C++ implementation, and the time and space complexity. Next episode, we'll look at a smarter sorting algorithm and see just how much better big O n log n really is compared to big O n squared. If this was helpful, hit the like button and subscribe. And if you have questions, drop them in the comments. I'll see you in the next one.